Okay, so today we're starting in medias res, in the middle, sort of in the middle of the story, and then we'll go to the beginning of the story in the 9 o'clock lecture. So, but that's okay. It's sort of a lot of life is like that. You sort of figure things out later. So what's the middle of the story? So the middle of the story is after we've introduced the general linear model, we solve it, and then we try to get a calculation of the significance of the response, and then we'll try to actually look at this in sort of a geometric view of what's going on. And I'm going over. This is taken from a paper by Tom Liu. So if you want to look up in the online thing, there's a paper by Liu et al. 2001. It's a nice paper, and so take a look at that paper for more of the details. But so what's the thing that we're going to go over in the main lecture? The thing we're going over in the main lecture is the general linear model. And so what does that look like? So we'll just write the general linear model here, and then the solution to the general linear model, and then the maximum likelihood solution to the general linear model, and then we'll look at how we calculate an F ratio in order to determine how much of the data do we actually explain, basically. So here's the general linear model. So basically, and this is all from the point of view of one voxel. So we're talking about this thing is a vector of image data from a single voxel. That's what that is. So that's data, time series, one vox. So you have to do this for every single voxel in the brain. So this is just a single voxel. So it's just a single set of brightness numbers for a voxel during an experiment. And so we're explaining that voxel time series by the following mess. And so this is that kind of brighter? Yeah, maybe that one's better. So what this is the way that you eventually get to thinking about these things. You sort of collapse this a large set of numbers down to just a few letters. So this is the data time series from one voxel, which it could be like 400 numbers, which is the brightness of that particular voxel over time. This thing is the experimental design matrix, and so what is that? That's actually, it's a matrix. So what that is and I'll talk about it in the main lecture, that's a convolution, a discrete convolution written out as a matrix. Because remember, when we do a convolution, we have to multiply, for each point in the output of the convolution, we have to multiply a bunch of numbers times a bunch of other numbers and then add them all up. So that's going to require a matrix to do that. And then here's one of the main unknowns, which is our hemodynamic response function. So this guy is our experimental design. So that's like when the stimulus is on and when it's, when the stimulus is on and when the stimulus, maybe there's two kinds of stimuli, when the two kinds of stimuli are on or off. They can be on at the same time. Okay, and then this guy is the hemodynamic response function. So that's what we're solving for, which is, what does the response look like? So the response could just be flat, which means like, this voxel didn't respond didn't respond to the actual stimulus. That's a possibility. And then there's many different ways of writing out this same thing, but the way that we're writing it out most explicitly is we've separated out our nuisance variables. And what are our nuisance variables? Those are things that actually occurred in the data. It's something that actually occurred in the data, but it's something that we're not interested in. And so an example might be a movement artifact. So a movement artifact will affect the time course a lot, just as much as, or even more than an actual response by the brain. But what we say is we're not interested in that movement. We don't care about that movement. We want to sort of get rid of it. And so some of our explanation of the data is going to be due to this matrix of nuisance variables. So these are nuisance. And those might be something like, say, a linear ramp. Like if the data just slowly gets brighter over time, maybe as a result of some movement, we want to allow that to explain part of the data. It's actually something that actually occurred, but we're not interested in it. And then these things right here are the weights. So the weights for the different nuisance variables. And that's a vector of weights. In the main lecture, I'll draw this out in detail so we can see exactly what all the parts are. And then finally, we've got the noise or the error. We'll just call this guy n here for noise. So that's a vector. So what is that? Well, that's kind of like what we couldn't explain because experimental design, after solving for a hemodynamic response function, will explain some of the data, the time course at this voxel. The nuisance will explain some of the other data, and then there's still some stuff that we can't explain, and so that's the noise or the error. You could think of that as the error too, but we'll just call it noise here. So that's our general linear model. And to explain, so it's linear. Why is it? Why is it linear? Well, we're just adding stuff. Everything just adds up nicely. And I'll talk in the main class what we mean by when we say linear. What does that actually mean? Okay, so that's our general linear model, which we haven't really sort of explained beyond these very generic things. And so how do we solve it? So what we want to solve it. One of the things we want to do is figure out what the hemodynamic response function is that fits in here after sort of allowing some of the data to be explained by this nuisance. And so there's different ways to solve it. And so the one we're talking about here is a maximum likelihood solution. And so we will assume white noise. I won't say what that is. We'll just say we assume a simple kind of a noise that's occurring. And then we'll do a maximum likelihood solution. And so what does that look like? So that looks like another pile of matrices. And so we're solving for the H. And so here's our solution to the H. So that's H hat, which means it's not the real H, but it's our best guess at it. And so what does that equal? So that equals another pile of matrices. So it equals our experimental design matrix transposed. And then times another matrix here, which is that's a perpendicular matrix, perpendicular projection matrix. We'll say what that is for the noise, and then multiplied by the experimental design matrix again, and then that whole thing inverted. So, inversion, you can sort of think of inversion like dividing. It's like a division-like process. So, that's the start, and then we multiply by the. We've got to sort of square this basically. So we multiply by the transpose of the experimental design matrix again, and then also multiply by this perpendicular projection matrix again, and then finally the data. Okay, so all of these guys are matrices. So we're talking thousands of numbers here. These guys are all matrices. This guy's a vector. So, and this guy is a vector. I'm sort of being overly verbose putting this in so we know what we're seeing, what we're looking at all the time. This guy's a vector also. So what is this mess? So first of all, what is this perpendicular projection guy? So this guy is where this guy, so here's the actual equation for that one. So that one is equal to the identity matrix minus the nuisance matrix times the transpose of the nuisance vector matrix inverted times the transpose again. So that was just a sort of so that's this guy. And so what is that thing? So that thing is basically, we want that to be the so it's a projection matrix. That removes part of data vector in that lies in the S space. So I haven't said what the sort of like what a space is. It's actually a space of possible time courses, and so we'll go over that. And so that's what this thing is. And so let's just back up. What's a projection matrix? So when you think of a matrix operating on a vector, what can it do? It can rotate it or shrink it or do both. And so a projection matrix might be something like you've got a vector here and you want to find this vector, the projection, like the perpendicular projection onto another vector. And so a matrix could do that. So you could have a matrix saying like, let's set up a matrix that will take that vector and generate this vector out of it. So that's a projection matrix. And you could do different kinds of projection matrices. You could try to find this vector. Like, what is that vector? So let's like turn this vector into that one. That's like, let's find the perpendicular. Let's find the perpendicular component relative to another vector versus find the parallel component. So this guy here is one of the perpendicular ones. That's what the perpendicular thing stands for here. So it's finding it's projecting, it's finding the component of this data vector that's perpendicular to this guy, as opposed to the component of that vector that is parallel to this other guy. And so in this, what I've drawn here, this guy is the S, the S space. This guy is the data vector. Okay, so that doesn't really make that much sense when you first hear it, but hopefully as it goes on, it will get a little better. Okay, so that's our solution. And so if you look at this, once you've done all these so one thing about why do we write out stuff like this? Well, it's like a shorthand for 20,000 or 30,000 numbers that are going into these 30,000 numbers over here are generating a small number, a couple hundred numbers here for our, not less than a couple hundred. It's going to be, this is the hemodynamic response function, so that might be, say, 10 numbers. So these like 30,000 numbers are going to generate these 10 numbers. Why do we look at it this way? Well, we can unpack those numbers into their matrices, and we'll do that in the main lecture. But after a while, what happens is you start to just do matrix algebra. So you just treat these things as just single units, and then you can sort of make matrix equations. So they're equations, like regular equations, that just have variables like x and y, except now the variables can be matrices, vectors and matrices. And they're kind of like regular equations. They're a little more fiddly in that a lot of times they don't commute. So like, x times y equals y times x, but that's not true with matrices. So you have to pay attention to the order that you do the multiplications in. But eventually, then you start operating at this higher level rather than thinking about all the 40,000 numbers that are involved. But what does this matrix say? Well, what does this matrix equation say? It says, here's our data. So here's our experimental design, which is something that we designed. And here's our nuisance variables, which we also designed. We said that there could be a linear drift, or maybe there could be there could be something in the data that looks like that, or there could be something in the data that looks like that. If you took the negative of that, then it would look like that. There could be something in the data that looked like, something in the data that looked like that. So we defined those. We put them into our nuisance matrix. So we defined the experimental design and the nuisance matrix, and then this thing, we know how to calculate that from stuff that we know. And so we do an inversion, this whole mess of operations, and that whole thing reduces to, this whole thing reduces to a matrix. Oops, one more. And then we multiply that matrix times a vector, and then we get another vector. So this thing is the hemodynamic response function for one voxel. And so what does that mean? That means like for one voxel, it's going to be a discrete set of numbers that describes how the signal went up and down like this over time. It might be 10 numbers, not too many numbers. So that's what we're solving for. And so once we've done this, we can just calculate this once, and then we just basically multiply it by the data vector, and we get our hemodynamic response function vector. So that's the solution. That was the solution to the maximum likelihood solution to the general linear model, which is, it's basically you can think of it as a deconvolution. So our experimental design matrix has been convolved with our hemodynamic response function, but that's an unknown, and we got some data. And so we've got data and what we did, the experimental design, and we're solving for what was the hemodynamic response. And the hemodynamic response, could have a shape like that, or it could just be flat, because that means like that particular experimental condition didn't cause any activation. Okay, so that's the solution. But then finally, what I'm going to talk about, sort of the main part, is the significance of the response, the statistical significance. And what is that calculation? So that's yet another pile of matrices. So these, so this is how we calculate the F ratio. And an F is a ratio of variances, of signal to noise, basically. So you have signal variance, variability, and noise variability. And if you've got a lot of variance in the signal versus the noise, then you've got a significant response. If they're sort of the same, then what you say is, this particular experimental design matrix didn't explain the variance that occurred in this single voxel. It's all for just one voxel. So we're doing this all, voxel by voxel. And so what is this significance equation? So it's got, some just numbers. So that's like the number of time points and the number of points in our hemodynamic response function, and the number of weights in our nuisance vector divided by the number of points in our hemodynamic response function, and then times this matrix mess. And so this one is a transpose of the data times some other projection matrices, which are different than this guy. So this one is one that involves the experimental design and the nuisance ones, and then one that just involves the nuisance ones. And since it's a variance, we gotta, it has to end up being squared. So we're gonna. So this particular order is done because, like I said, you have to do things in the correct order when you have matrices and vectors. A lot of things don't necessarily commute, and so when you want to square something, you're going to take the transpose of it and then multiply it by the not transpose of it afterwards, and then you have to have the matrices in between. So that's our signal. I haven't explained what those guys are yet, but I'll write them out in a sec. And then that's divided by the transpose of the identity matrix minus this PXS projection matrix times the Y again. Okay, so what we want to do now is try to get a sort of a geometric idea of what that is. Of what that sort of F ratio is trying to tell us. Okay, and so there's two additional, let's just take a look at this matrix equation down here. So this one, so one of the things you can do with a matrix equation, you can distribute it. So matrix equations, you can use the distributive rule. So to expand this thing out, what is that? You could say that's identity matrix times Y, so that's basically Y, minus this projection matrix times Y. So you can sort of you can think of matrix equations just like regular equations, except you got to be careful about the order. So what are those additional matrices in words, and then we'll try to draw them out in sort of geometry. So put that in red. Okay, so the first guy is the PXS. So where should I put these? Put it down here. So PXS. So that guy is so projects data onto experiment plus nuisance. And I haven't explained why we're sort of so obsessed about nuisance versus experiment. I will in a sec. So that projects data. So that's the parallel projection or oblique projection, as it may turn out, onto that's how much of the data is actually explained by a combination of the nuisance as well as our experimental design. And then the P, as opposed to this perpendicular one, which was like, what is kind of the opposite? It's kind of the opposite of how much data was explained, is how much data wasn't explained. So, but this one here is, projects data, onto just nuisance. Okay, so that's these guys here. So that guy and this one here. Okay, so what does this sort of talk about space? So what kind of weird space are we talking about? So normally when we talk about space, you think of like XYZ space. So at least I do. So we have, call this X, Y, Z. And you've got some vector in this space, and that vector has, it has X and Y components and Z components. And it just points different positions within the space. Now, what are we, what kind of space are we talking about here? So what we're talking about is a space that contains different time courses. So that's really, so our X matrix here has a bunch of columns in it. So that's our X matrix, a bunch of columns in it. And what are those columns? Those columns are, these columns are the basis vector vectors of experimental design space. But what's in the space? So what's in the space are basically time courses. So different points in the space. So instead of just like thinking of it as just sort of different points in where it's somewhere in 3D space, what we're thinking about at each point in the space, there's a particular time course. And so, what does that mean? So let's just take a very simple two-dimensional case so you can really get it concrete. So say we have one basis vector that has a time course of 0 and then 1. And then we have another basis vector that has a time course of 1 and then 0. And so so if we just think of a two-dimensional space of that, we can think of, here's 1, 0 basis vector for our space of possible time courses, and here's basis vector 0, 1 for our possible time courses. And so what is in that space? Well, if you go someplace in that space, like here, like that means you're going to get something like 1.5 and say 1. So that's a possible time course, 1.5 followed by 1, that is in this space of possible time courses. So that space defines a whole bunch of time courses. They could be like 1, 0, that's in the space. 1, 1, that's in the space. 20, 20, that's in the space. So, but there's something that's not in the space. And what's something that's not in the space? Well, imagine you had another dimension. and maybe the vector was sort of going into the cube like that. That has some parts that are in the space, but some parts that are not, like that are going in the third dimension that's not in the space. And so so you could have a time course that is actually sort of not in your space. And so that's the way that you think about this matrix of the experimental design. It defines a space of possible time courses. So there's certain time courses that we can explain, and there's other ones that we can't explain. We can explain part of them, but we can't explain all of them, and hence the need for noise. So noise is going to absorb any part of the data that we can't explain with this space of any possible time course. And so we have the same kind of thing, for the S matrix. There's a set of there's some column vectors that define the basis of the set of time courses that the nuisance matrix can explain. So why are we sort of like so obsessed about sort of the nuisance, this nuisance space versus the experimental design space? And one of the problems is that those two spaces might not be perpendicular to each other. And so what does that mean? In words, they might be correlated with each other. So sort of being not perpendicular is equivalent to correlated. And completely perpendicular, orthogonal, is equivalent to completely uncorrelated. And why is that a problem? Well, an example might be, here's our experimental design. And say our experimental design is something like very simple. So we just have the stimulus, it's only one stimulus type, but the stimulus is off, and then we turn it on, and then we turn it off, and then we turn it on, and then we're done. So that's our experimental design. Now, say we've got a nuisance variable, which is just a linear ramp. So here's a linear ramp like that. And that could easily happen. You slowly sunk down into the cushion a little bit, and it slightly moved a voxel that had a little bit more air in it, and so that voxel got brighter and brighter and brighter, or dimmer and dimmer and dimmer. So let's just take a look at that, and let's just correlate those two with each other. And if they were perpendicular to each other, those two spaces were perpendicular to each other, then the correlation between them should be 0. And so what is the correlation? Well, just multiply all these guys times each other, multiply all those numbers across that whole thing, and what do you get? You get something that looks like, so here's the core of those two. You get something that's, you're multiplying by 0, and so it's 0 up until here, and then so it's 0 up until here, and then now you're multiplying by a negative number, and then you get back to 0, and then it's 0 again, and then you're multiplying by a positive number like that. So that's what your correlation looks like. And then how do we calculate the correlation? We multiply all those pairs and then sum everything up. So when you sum that up, you don't get 0. You get a positive number. And why is that? Well, if you just look at the experimental design, it's kind of a little bit on that side, isn't it? Just like the linear ramp. Like the linear ramp is kind of like, as you go to this side, it goes up. And same with this guy. As you go to this side, it kind of goes up a little bit. And so there's an example, a very simple example of how a linear ramp is correlated with your experimental design. And so now what? Now who gets to explain the data? And so that's kind of what our problem is. There's also, if you read in the paper, you'll see there's a lot about oblique projections. Let's just sort of quickly define what that is. And so if you have a space, two spaces that are perpendicular to each other, and then you've got some data. So here's a data vector. You can sort of cleanly calculate the perpendicular projection onto that. You can say this is how much of the data vector the experimental design matrix can explain. But you can also have a situation, what if they're not perpendicular to each other? So if they're not perpendicular to each other, which is the general case, then what's going to happen, and we've got a data vector here, then we have to do an oblique projection, and the oblique projection is not perpendicular, it just make it parallel to this guy. So if you make that parallel to that guy, then you can figure out, like, that's how much of the data vector the experimental design matrix can explain. So there's some oblique projections going on there. Okay, so so now let's just try to let's draw this mess out down here. Just try to see, what the different parts of that are. And so the first problem is the one I described up here that I'm just erasing now, which is that the data doesn't have to be in the experimental design matrix. It's possible the data could do something, make a time course that the experimental design matrix can't explain very easily. It could, you could be thinking, I'm just thinking, and it's causing the voxel to do something, and it's completely unrelated to what the experimental design can explain. Like the experimental design said, there's nothing, now there's a face, then there's nothing, and there's a face, and I'm just thinking about lunch. And so that's completely unrelated to the face and could cause some kind of pattern of activity that's not explainable by nothing in a face, nothing in a face. So we have to deal with that problem. So let's sort of draw out our giant. But the problem is, these are all like 10,000 dimensional spaces, but we're going to draw them out as just 2D. Okay, so here's our space, our 2D space. And so what is the 2D space? This is the total space that the experimental design and the nuisance can explain. So that's our starting point, and so now we've got some data. So here's a data vector, and we'll draw this data vector sticking out. Okay, so that's our data vector. So the data vector doesn't have to be in this, it can sort of stick out of the experimental design, and also nuisance vector, also nuisance space. And so it might that you're just thinking about what you're going to get for lunch while they're showing you faces. So now we have our sort of coordinates within that are within the space, and so this is our unit S vector or direction or multiple directions, but we'll just do 2D. So we've got sort of a 2D space that includes everything that the experimental design and the nuisance can explain, but then we've got another dimension sticking out because the data doesn't have to be in that space. Okay, so we got that direction, and then we got this direction for our unit experimental design vector. And so then we have our oblique projection, because this guy, so this guy is our oblique projection onto of data, oblique projection of data onto our S vector, and the vector that does that is another vector which I haven't even drawn in there, which is E onto S. So what that vector will do is an oblique projection vector that will projection matrix that will take the Y vector and project it down to the unit S vector, just explaining what the unit S vector does, because it's not necessarily a right angle between the unit experimental design vector and the unit nuisance vector. And we got the same thing for, see, make sure I get these. Okay, yeah, that's going to be still in the plane. Okay, so here's the same thing, the same kind of oblique projection vector for oblique projection matrix of data onto experimental design. That's oblique being parallel to the S, like project onto the X vector, but stay parallel to the S because the S and the X are not perpendicular to each other, correlated with each other, like, for instance, that example, simple example of a linear ramp. So that's this guy. And that's going to be a P, this E for oblique projection vector. So that will take the data vector, and that matrix will sort of like obliquely project it down, onto the experimental design matrix. And then we could add those two together and get this other one, which is an important one. And this is all of the data that we can explain. So this is orthogonal projection of the orthogonal projection data onto XS space. And so this guy is orthogonal XS multiplying the Y vector to project it into the plane of things that we can explain. So this guy goes up to here. There's another vector that goes up to here, and this one is perpendicular. So now we're saying, let's take our data vector and just plop it down into the plane and find out how much of it we can explain that is in the total set of time courses that are possibly generatable by the experimental design and the nuisance. Okay, but we still aren't to this. So we've got only two more to go. So we've got another one up here. So this guy is perpendicular to that guy. And then we have one more that's perpendicular to the X. Hopefully I don't get that in the way. So we'll put it here. I'll dash it so it's... And then there's just one left. So that guy's perpendicular to there. And And then finally, last but not least, the one we're really interested in, which is over there, and that is this guy here. And this guy is perpendicular to that one. Okay, so what is that most important one here? So this one is, so how much more of data we can explain by adding experimental design. And so this is our F numerator. And it's basically, equal to, we perpendicularly project, this is the one that perpendicularly projects into this experimental design and nuisance, but we've subtracted off the perpendicular projection just into the nuisance vector. And so what is that geometrically? So let's make sure we label. So this guy, and then and before I go any further, this guy is the error or the noise. Okay, error, noise. So that's how much stuff is not explained by either the nuisance or the experimental design, and so let's just what was I going to do? And so what is that guy? So that's basically the error, not explained by experimental design and nuisance. And this is the F denominator. And what is that? That was, the identity matrix, minus this projection matrix of both experimental design and nuisance times that data vector. So you could look at that as, if you distribute that, it's the data vector minus the data vector projected into the perpendicularly projected into the xy plane. So let's just look at that geometrically here. So it's the data vector here minus this projection into the plane. And what's the projection into the plane? That's this guy down here. And so if you take this guy minus that guy, you get the error. So that guy is so just look at it just completely geometrically. So you're just, it's the data minus the perpendicular projection of the data into this thing, and that's the difference. That's the error, the difference between them. And you could do the same thing over here. So what this says is operate on the y vector with the perpendicular projection into x and s, and that gives you this vector right here, and then subtract off the perpendicular projection into the nuisance. So here's the nuisance, and the perpendicular projection into the nuisance is this guy right here. So that guy right there is perpendicular projection of the data into the nuisance. And so if we subtract those two, what is that? That gives us this guy right here. And that's how much more data that we can explain that's completely uncorrelated, perpendicular to the nuisance data, the amount that we can explain with the nuisance. And so that's our numerator. And so this takes care of the problem of the fact that our experimental design and our nuisance are not necessarily completely uncorrelated. They might be quite correlated. So, so for better or for worse, so if you look in the paper, Tom Liu has a drawing of this, but he didn't include all the different vectors. Maybe there was a reason for that. But I'd like to have them all in there so I know exactly what we're talking about. So this thing right here is an illustration of how you calculate the F ratio. So basically, it's all the same except you're squaring it, and so that's why there's an extra y. But if you look at before we square it, what you're doing is you take the projection of the data vector into the experimental design plus nuisance space, and then you subtract off the projection into the nuisance in order to just find how much additional things we can explain that are completely uncorrelated with the nuisance, so that we don't want the nuisance contaminating our actual estimate of how good the response was, because unfortunately it's correlated with our experimental design. And then, so that's the numerator, and then the denominator is basically just the error. And the error is just the identity matrix, which is just basically the y vector minus the projection into the plane of stuff we can explain. So here's the the y vector, and we just basically project that down here and find this guy, and this guy is the data that we can explain. And so that forms the numerator, or the noise, basically, because when you subtract those two, you get this vector here, which is the error vector. So there you have it. So that's one way of trying to deal with the fact that your nuisance vectors might be partly correlated with your experimental design vectors. And we'll take that into consideration and don't allow any of the nuisance vectors to explain the actual data. And these are real practical problems that are all sort of out there in the literature, and people don't always sort of do things the right way. And this is just one out of thousands of papers in this area, but this is a pretty clear one that sort of goes over some of the problems that you have with designing these experiments. And if you go into the later parts of this paper, some of the practical things that you can get out of it are looking at different experimental design types. And so one of the things you might have heard of is that you have block design versus event-related design. So you can have so if you do a GLM, some people do something called a block design, but you could also do event-related design. Those two things are basically the same. So the analysis that you use, that I just erased here for doing this, the solution to this thing, is no different between those two. And so what is the actual difference? So if you do a block design, typically what you do is you have, one condition on for a while. But how do we actually imagine that? Well, we just imagine we turn condition A on, and then we turned it on again, and then we turned it on again, and again and again. So for 15 seconds. So basically, but that's just a bunch of impulses all lined up next to each other, and then we turned it off. So what happens when we look at the response to that? We're going to have a hemodynamic response function, which is relatively small at this scale, say something about like that. The hemodynamic response function, a block design will be defined by blocks that are longer than the hemodynamic response function. So we have the hemodynamic response function might be sort of something like that, 5 seconds, and the block is 15 seconds. So when we convolve that thing with, when we do this operation here, x times the hemodynamic response function, what are we going to get? Well, we'll get something that's, that's completely flat, and then it goes up like this, and then eventually it gets up to a flat plateau, and then when you turn it off, it takes a little while for it to die off. And what does the data look like? So what does the y look like? So this is, this guy is the, this guy is the x, and this guy is the, xh. But what does the y look like? Well, the y, it's going to be, considerably noisier than that. So what's going to happen is, you're breathing and your heart is beating, and then it goes up a little bit. Maybe, you made a movement, and then, it eventually goes down a little bit, something like that. So that will be the actual data. Now, we could compare and this is what we would call, block. And so what would event-related look like? So event-related would look like, let's just do a bunch of short events. So the x for an event-related one was, we do something, condition A, and maybe do condition B, go back to A, maybe B, maybe wait a little bit longer, something like that. So say this is, condition A, B, maybe B again, and then A, maybe A again. And what does that data look like? Well, first of all, what does the experimental design look like after we've, done our solution or just assumed whatever the hemodynamic response function is? So that's going to, look like, something like it comes up, and then we have a different hemodynamic response function for B, and then it goes down, and then maybe up again, and goes down, and then, up again, something like that. And then what does our data look like in this case? So here's our y. Well, you're breathing, and there's heartbeat, and then you get a little bit of a junk response, and then another little bit of a junk response, and then maybe up and down, and then you made a little movement, and then it kind of looks something like that. That's actually a pretty accurate diagram of what the data looks like. And so it turns out that if you look at how these different design matrices perform, this case is better for detect. So if you just want to detect whether a response occurred, it's better to do it this way. And why is that? Well, because you've got a substantial, you can see like, wow, I can actually look at the data and see the response in the data. Whereas here you've got to average, the data looks like a mess. You just have to average many copies of that very noisy response in order to detect it. And so you can go through the equations and show that if you just want to detect whether a response occurred or yes or no, this is actually better. But it's worse for trying to estimate what the hemodynamic response function looks like. Worse for, estimating HDR shape. And why is that? Well, that's pretty obvious, because the only way you can estimate the hemodynamic response function shape is at the very beginning and the end of the blocks. And it's particularly hard if you're not overlapping the blocks to sort of distinguish the hemodynamic response functions of the different conditions. Now, if you go down to this case, we've got all different kinds of overlap between these hemodynamic response functions being played out. And so this one is better for HDR shape and worse for detect. So that's important to keep in mind. So if you're going to do something that's actually a event-related design, your ability to detect whether or not something has happened is going to be reduced considerably versus doing a block design. So this is event-related. We'll put it in quotes because they're basically the same thing. Now, there's other reasons why you might want to do event-related. Maybe you can't arrange your paradigm to have like 20 copies of a particular kind of a stimulus, because if you're doing sentences or some other kind of thing, there's a constraint. You have to do it this way. So I'm not saying that block design is better. I mean, there's a lot of things that just can't be done in block design. But it's important to sort of keep in mind that if you have a choice and you're mainly interested in detecting whether or not a brain area has responded, this one is actually going to be more efficient for detecting it. It's not that you couldn't detect it with this. You just have to collect more data. So those are the kinds of higher order things that you can try to use an analysis, use the solutions that we looked at here, and see how they perform in different sort of experimental design situations. So you can see it's like a very general way of looking at the data. There's no difference between a block-related and event-related. Really, the only difference is just like what the design matrix looks like. But the actual math and all this nightmare here for calculating the significance, numerator over the denominator for the F ratio, all that's exactly the same between the two. Okay, so that was, for better or for worse, we've come to the end there. Any questions at the bitter end about this? Did I label all the vectors? Yeah, I think I did. I forgot to label this one. So this is orthogonal project data onto XS. So both of those. Yeah. I think I got all the other ones. Yeah. Okay, so I don't know if that helped at all, but for me it helps to sort of have some idea of geometrically of what's actually going on. And some of the conclusions are just common sense conclusions that, it makes sense that if you're trying to sort of look at the hemodynamic response function shape, you just need a lot of different samples with different amounts of overlap. And so that's why you do kind of random. I mean, all these things kind of interact with your experimental design. So one of the problems is if you look at an experiment where you're jittering, you're essentially making random amounts of time in between different types of events, that can get kind of irritating to the subject. It's like, you're doing this, and then, oh, it just waits for a while, and then this. And it's kind of, so there's, if you jitter a lot to get like a good estimate, then it gets really irritating. So all these things sort of play off against each other, and you can't really win in the end, if you're going to do this, you're just going to have to collect more data than if you do a block design. And you try to sort of make the experimental design matrix as columns as orthogonal as you can, but you can't make them that orthogonal without making your experiment a lot longer. And so you just do the best you can. Okay, well, so much for the general linear model. It was just a kind of an overview, just to get some feeling that it can be understood. And like I said, there's lots of different variations on a theme here. This was just one presentation, but it's just to try to give an introduction to the complicated field of very simple analysis methods that are not true. Okay, I think we'll stop there, David.